Hello and welcome. Today we're going to do something a little different. We're going to deconstruct a set of exam questions to really get our heads around the physics that not only keeps the Hubble Space Telescope up in the sky, but lets it see to the very edges of the universe.
All right, let's just dive right in. I want you to think of this as a mission debrief. Every exam question we tackle is an objective we need to clear to really understand how Hubble works, from the basics of its orbit to the absolutely mind-bending things it's discovered.
Okay, so mission objective number 1. It's a simple one, but it's absolutely crucial. We've got to correctly identify what the Hubble Space Telescope even is, in proper astronomical terms.
So, here it is, our first objective, taken straight from the exam paper. Now, it might seem really basic, but in physics, getting the terminology right is the launch pad for everything that comes next. So, what do we call something that orbits a planet?
And the answer, word for word from the mark scheme, is a satellite. Now, you could also say an artificial satellite, and that's probably a better answer. I mean, the moon is a natural satellite, right? But Hubble was built and launched by us, making it our most famous eye in the sky. And just like that, Objective 1 is complete. Okay, Objective 1 is down. Time for number 2. We need to establish a comms link. Because think about it, if Hubble can't phone home, all those incredible pictures are just stuck up there. To figure out how it sends all that data back, we need to understand the waves it uses.
And boom, mission control hits us with a calculation. So Hubble uses microwaves, we're told the wavelength, and we're told the speed, but we need to figure out the frequency. This is a classic wave equation problem. Let's get into it. Now, before you start plugging numbers into a calculator, there's a classic trap hiding in this question. You gotta look at your units. The wave speed is in meters per second, but the wavelength is in centimeters. They don't match. So our very first step before anything else is to convert those 12.5 centimeters into meters. So here's our game plan. Step 1, convert the wavelength. 12.5 centimeters becomes 0.125 meters. Easy enough. Step 2, we grab the right tool for the job, the wave speed equation. Step 3, we just need to rearrange it a bit to solve for frequency. And finally, step 4, we plug our numbers in and see what we get. It's a really clear, logical path. And when you run the numbers, you get this, 2.4 times 10 to the power of 9 hertz. Or, to put it another way, 2.4 gigahertz. That is the frequency Hubble uses to call home. Comms link established. Objective 2, check. All right, we're making good time. On to our third objective. We know Hubble is orbiting the Earth, and we know our planet's massive gravity is constantly pulling on it. So that leads to a pretty big question, right? Why doesn't it just fall out of the sky? This question gets to the heart of it. It's all about the delicate dance of orbital mechanics. Let's break down exactly what gravity is doing to Hubble's motion up there. The secret is that Hubble is moving incredibly fast, but sideways. So as gravity pulls it down, its forward speed means it constantly misses the Earth. This constant inward tug from gravity is what we call the centripetal force, and it's what bends Hubble's straight path into a circle, an orbit. Think about swinging a ball on a string over your head. The string is constantly pulling the ball inwards, right? That's what keeps it going in a circle. For Hubble, gravity is the string. And here's the really crucial part, straight from the mark scheme. Gravity is always pulling at a right angle, at 90 degrees, to the direction Hubble is moving. This means the force doesn't work like a gas pedal or a brake. It works like a steering wheel. It doesn't change Hubble's speed, but it is constantly changing its direction. So its speed is constant, but its velocity, which is speed and direction, is always changing. And with that, Objective 3 is a success. Okay, we've figured out how Hubble stays up there. Now for our final and honestly, most exciting objective. We're going to analyze the actual data it sends back and see, with our own eyes, one of the most profound discoveries in human history, the fact that the universe is expanding. So our final mission is to play astrophysicist. We've got the visible light spectra from our own sun and from two very distant galaxies, A and B. What secrets are hiding in this data? Okay, take a good look at the evidence on screen. Each spectrum has a unique pattern of dark lines. You can think of these like cosmic fingerprints. They're called absorption lines, and they tell us what stars are made of. Now look closely at the pattern for the sun, and then compare it to the patterns for galaxy A and galaxy B. And this is it. This is the key observation. The pattern of lines for the galaxies is exactly the same as the sun's. But for both galaxies, the whole pattern has been shifted over to the right, towards the red, longer wavelength end of the spectrum. This right here, this is the legendary phenomenon known as redshift. So what does this red shift tell us? Well, it leads to two absolutely mind-blowing conclusions. First, that shift towards red means both galaxies are moving away from us. It's just like the sound of an ambulance siren changing pitch as it drives away from you, but with light instead of sound. Second, the amount of the shift tells us the speed. Galaxy B's lines are shifted more to the red than Galaxy A's, which means it's flying away from us even faster. This is the evidence that proved we live in an expanding universe. It's just incredible. Final objective, complete.
So, let's just quickly recap our mission debrief. We started by simply defining what a satellite is. Then we calculated its communication frequency, we explained the physics that keeps it in orbit, and finally, we interpreted its data to see the universe itself expanding before our eyes.
And you know, that's the real takeaway here. These questions, they're not just some abstract problems on an exam paper. They represent the actual real-world physics and the fundamental rules that scientists and engineers use every single day to explore the cosmos. Which leaves us with one last, pretty deep thought to ponder. If Hubble and other telescopes show us that pretty much every galaxy is racing away from every other galaxy, what does that imply about the future? What is the ultimate destiny of a universe that just keeps on expanding? Now that's something to think about.